In this tutorial, I am going to show you how you can quantify RNA Seq rates using the tool FeatureCounts. So what we are going to do is to perform these three activities. We are first going to get our data. So we will download the sequence reads, and we're also going to download our reference sequence. And after that, we will map the reads to the reference sequence, and we will quantify the mapped reads. Please take note that these three activities are part of a bigger workflow that is used for RNA-seq data analysis. And so this means that there is more to what I've indicated here when it comes to RNA-seq data analysis. But the focus of this tutorial is to show you how to quantify the reads, and that is why I have limited the activities to these three. Okay, so that's what you need to know. And I've covered one such tutorial where I showed how to perform RNA-seq data analysis. And there are different tools available. So that means the workflows change slightly when it comes to RNA-seq data analysis. So you can start by watching that video, which I use HiSAT and other tools to perform RNA-seq data analysis. And I'll be making more tutorials on that. So make sure to come back and watch more RNA-seq data analysis in the future. The link to that video I made mention of about the RNA-seq data analysis is available in the description box. So make sure to check that video out. Now, if you want to follow this tutorial, you need to make sure your PC satisfies these requirements. You should have a PC with a RAM greater than 8 GB. And you should also have the number of cores of your PC not less than 8. For the software, you should have a Linux or MacOS operating system, and you should have star installed. We'll use star to map the reads to the reference sequence. You should also have FeatureCount installed. FeatureCount will be used to assign the reads to the gens or quantify the gens. And we are going to use multi-QC to aggregate the results that FeatureCount will generate. Instructions for installing these tools can be found in the description box. Okay, I've made tutorials, I've made videos that show how to install these tools. So check the description box for the links and then use them. Alternatively, you can use Anaconda to install these tools. So if you have Anaconda installed, you can use that to also install the tool. That's fine. So I'll show you how to use Anaconda to install these tools, by the way. So that's what we are going to do. So just check the description box. You'll find all the necessary information that is required in order for you to follow and reproduce this tutorial. So let's get started. This video is based on this Galaxy tutorial. I will leave the link to this page in the description box. So in this tutorial, the authors showed how to perform reference-based RNA-seq data analysis. Okay, so that's what this tutorial is about. But I am going to cover mapping and then the counting of the number of reads. For the mapping, I will skip the inspection of the mapping results. I've already covered that in a separate tutorial. So I suggest you watch that tutorial. In that tutorial, I showed how to perform quality control, how to map the reads, and how to also spread the reads or visualize the reads using IGV. So I think that will also be a good start for you. So that's it. So for this tutorial, we are going to get the data, perform the mapping, and move straight to counting of the number of reads. So that's what we are going to do. So let's get started. So first of all, let's look at the data. We are going to use these fastq files. Let's check them. Yeah, these are smaller ones. We are going to use these ones. And then we are also going to use the reference sequence. Now, for this data, we are dealing with this organism, Drosophila melanogaster. So the sequence reads are for this organism. So take note of that. So we will need to also get a reference sequence. So we will need a fastq file and then the DTF file. I think the DTF file, we can find the link somewhere here. I found it here. Let's scroll down. The link is here. So we have it here. And then for the fastq file, we will check it on the UCSC website. So this is the UCSC page where we can download the fastq file. I'll leave the link to this page, and I'll also leave the link to this page in the description box. So that's what we are going to do. Now, because we have a couple of files, what we are going to do is to get all the links into a script. We will write a script that will download all the necessary files for us. So what we need to do is to get the download links, and then we will use that to download the necessary files. So let's go back to a terminal and then prepare our environment. Okay, we are on the terminal now. So what we will do first is to create a working directory. So we will say make the RNA Seq, and then we are going to cd into it. And so this means that files that we will generate will all be stored or saved in the directory. And it's important we do this because we would like to separate all the files that we are going to generate from files that are already on our PC. Okay, so now we have created it, we have seeded into it. So what we are going to do next is to download the necessary files. So first of all, let's go back. We need to organize our links. So let's go back to the various web pages or the various places where we can get the download links. Okay, so we will start with the Galaxy page where we have the files we will need. We will use these files. We have 2 samples here. Then we also have our GTF, which is the reference sequence here. Then we also have our fastq file, which is here, this one here. So we are going to get all these files. So we need to get the links. So first of all, let's go back to the terminal. And then on the terminal, we are going to create a script. And in that script, we will place all the links and then execute that script. So we will do a batch download here. So I'll say nano download data.sh. I'm using nano, but you can also use VI or any text editor for that matter. So take note of that. So I'll open it and then I'll go and then bring all my links. So I'll start with the Galaxy platform. I'll check the files I have. I'll use these files. So I'll copy all the links and then I'll paste them here. So I have my scripts opened. I'm going to edit. So I'll paste the links there. These are the links. I'm going to use wget to download. So I'll just place wget here just to get them there. I have them like this. So let's continue. So we have wget, but there is something else I would like to do, and that is to modify these names here. So I'm going to download them all right, but I'll also rename them so that I have shorter names. So what I'm going to do is to keep only these ones, the ID here and then the one, which is used to distinguish between the forward and the reverse. We are dealing with paired and reads. So I'll, this one, for example, I'll say -o, and then I'll put that name there, and I'll say fastq sanga on somewhere. Let me do this. Let me decrease the text size a bit. Okay, now it's okay now. So I'll do same for this. So -o. I'll paste this here. I'll say fastq sanga just to keep them. I'll do same for this. Then I'll do same for this. Please note that this O is uppercase. Okay, so I have them there. You should also know that what I've done here, there is a better way of automating the download process, but because I'm assuming that some of the viewers may be beginners, that is why I'm trying to make it in this way so that you can understand whatever I'm doing. But there are ways to automate this process, okay, without you having to specify wget every time. But these are things that will be good for advanced people, but that's something that we'll cover in another tutorial. But if you're also interested in automating some Linux activities, you can always reach out to me. I will leave my contact in the description box. Now let's get the reference sequence. You will need the fastq file and then the DTF. So let's go and get the download links. Okay, so let's first get the DTF, which is here. Should be somewhere here. Yeah, this one. We will get this link here. Or actually, let's do it this way. We don't need to use the DTF here. We can still use the one here, the one in this particular web page. Ideally, it's advisable to download the fastq and the DTF from the same database. So I'll download everything here. I think that should be better. So let's download the ones here. So we get the fastq and then the DTF. So the DTF can be found in the gens directory. So first of all, let's get this link. We'll right click and then copy the link. And then we will paste it here. So I'll say wget and then I'll paste the link there. Then let's get a DTF. So when we are here, just search for gens, this one here, click it, and then you will see the DTF, which is here, dm6.ensgen.dtf.gz. So let's get this one, right click, then copy the link. And then you can paste it here. So I'll say wget, and then I'll paste the link here. So this is the link for the DTF file. So that's it. So let's save the changes. And then let's execute the script. Now with the execution, you can use bash like this and then call the script and execute it. Or you can also use this approach where you say slash. You can do it this way. I prefer to do it this way. So if I'm going to do it this way, then I need to modify the script again. I'll use this opportunity to show you a couple of things when it comes to writing scripts. So I'll go back again. I'll say nano. I'll edit the script here. Then the first line here, I'll say /bin/bash. So this tells Linux that whenever we execute the scripts, bash should be used to run the commands here. That's basically what this means, the shebang line. So I'll exit the script again. I've made the changes. Now I'm going to add execution rights. So I'll say chmod +x. I'll say download data.sh. So I'll have it done this way. So now let's do an ls. We should find download data.sh here. Okay, so now we can download the data. So I'll use // now call it this way, but you can also use bash and then also call it. So whichever one is appropriate, use that one, but I'll do this // and I'll download the data. So let's download the data now. Okay, so the files are currently being downloaded. Okay, all the files have been downloaded. So let's check them out. Let's do an ls and then check the files. So we have our fastq files here. We also have the reference sequence, the DTF and then the fastq. These two files, you can see that the extensions are .gz. That means that they have been compressed. So we will process them. Now we are going to place the fastq files in another directory. So let's create a directory. We will say make the data. And then we are going to say make the data slash fastq. I'm doing just so that I can group my files. Okay, it also makes my work more organized, and it's easy to locate files if you have naming conventions, and if you also have folders that you can put them in. So I'll move all the fastq files into this directory. So I'll say mv, and I'll say gsm. Let me use gsm, and I'll say star. So all files that begin with gsm will be moved, and we can see that we have 4 files. 1, 2, 3, 4. These are the fastq files. So I'll move them to data slash fastq. So now if I do an ls into data slash fastq, I should see them there. Okay, so that's what we have done now. So we have our fastq files ready. Now let's work on the reference sequence. Let's do an ls again. Of course, we will see this directory, but we are going to look at our reference sequence here. We have the DTF, we also have the fastq file. These are gzip, they are compressed, so we need to decompress them or uncompress. So we will first start with the DTF here. So we say unzip dm6.ens, and then we complete the name. So let's uncompress this. So we are using the unzip utility. So now let's do an ls, and you will see that it has been uncompressed, and that is why it no longer has the .gz as an extension. Let's work on the fastq file. We say unzip dm6.fa.gz. So let's run this command. That has also been done. So we can do an ls and then see that's there. Let's do one more thing. I normally prefer to have a naming convention for my files. So what I'm going to do next is to rename this DTF file here. I am going to remove this name here, the ENSGen. I will remove that so that we can have the same base name for the reference sequences, and then these names will be followed by their respective extensions. So I will do that as well. So I'll rename this one here. So I'll say mv dm6.ensgen.dtf, and I'll say dm6.gtf. So let's do an ls, and you will see that's there. So now we have these 2 files, which are also good. So we are going to move these files also into this directory. So we will create a directory called ref. So I will say make the data slash ref, and then I'll move these files there. So I'll say mv dm6 star. I'll say data slash ref. So they have been moved there. So that is good. Now let's check those files also out. So let's do an ls, and let's say ls data. You will see the ref directory there. So now we are going to say ls data. Let's do it again. We will say ls data slash ref, and then we will have our files there. So now we have our files ready. So it's time to proceed with the next activity. So let's continue. I am now going to show you how to install the tools using Anaconda. So first of all, make sure you have installed Anaconda. Instructions for installing Anaconda can be found in the description box. So after installing Anaconda, the next thing you have to do is to add Conda channels. We will add 2 channels. So I'll start with the first one, which is Bioconda. So I'll say Conda config add channels, and I'll say Bioconda. I'll add a second one. So I'll say Conda config add channels, and I'll say Conda forge. You can also confirm if the channels have been added. So you can say Conda config show channels. This will list the channels. So we have Conda forge, we have Bioconda. The default channel comes packaged with Conda, so we will leave it as it is. We are now going to install the tools. So we will first create an environment and install the tools in that environment. So we will say Conda create -n, and I will say RNA Seq. So the name of the environment is RNA Seq. We are now going to specify the tools that we want to install. So we will start with star, and I also say subread. FeatureCounts is part of the subread package, so we are using subread. We are also going to install multiqc. So now we can run this command. We will now type Y to confirm, and then Conda will download all the necessary packages and install them for us. So let's wait for Conda to complete its work. Okay, the packages have been installed. So if you want to use the tools, you need to activate the environment. So you have to use this one here. And if you are done, you can deactivate using this one. So let's test the tools first. So if you want to test the tools, you need to first activate the environment. So you can say conda activate RNA Seq. And this will activate the environment. So after that, you can test. So let's just start. We will start with star like this, and then we can run it. We can also check where star is located, which is here. That's fine. So once you run it and you have this, that means that the tool is working. Okay, so we've tested with one. You can also do for FeatureCount like this and then run it. So that's also done. So that is how we install the tool. So once you are done with the installation, then you can proceed with the other activities. So let's continue. What we are going to do next is to map the RNA sequence to the reference sequence. We are going to use star to do this. If you are going to use star to map RNA sequence to a reference sequence, you need to first generate a genome index. So let's go to the star documentation page and look at the instructions we can use to generate our genome index. We are on the page now. I'll leave the link to this page in the description box. So when you are here, scroll down to this section, generating genome indexes. So if you want to generate a genome index, you need to first call star, and then you indicate the options here. Some of the options are mandatory, some of them are optional. So let's take a look at the options here. We have run thread n, which is used to specify the number of threads. We have run mode, then you indicate genome generate. This is compulsory, it's mandatory, you have to specify that. We also have genome dar, which is used to specify a directory, and this directory is where star will save or store the output files. We also have genome fastq files, and this is used to specify the fastq file that you will use. If you have more than one fastq file, you have to specify all of them. So file 1 space file 2 space file 3 in that order. We also have sjdb gtf file, which is used to specify the gtf file. This one is not compulsory, but it's recommended. If you have the GTF file, it's recommended to specify that. We also have sjdb overhang. Here, I will skip this one. I will not include this. I will use the default value. So what we are going to do next is to go back to the terminal and then write a script. The script will contain the star command that we will use to generate the genome index. So let's go to the terminal. We are in the terminal now. What we are going to do is to create a directory called index. So this directory is where star will save or store the output files. So we will say make the index. Let's do an ls to check the directory. So we have that here. Now we are going to create a script which we'll use to generate the genome index. So I'll use nano, but you can use any text editor of your choice. So I'll say nano, and I'll say generate index.sh. I'll execute this command, and then I'll start with my shebang line. Then I'll say star. I'll indicate the number of threads, which is 8. I'll use the slash and then move to the next line. I'll indicate my run mode, which is genome generates. I'll indicate my genome DAR, which is this one here. And I'll say index. I'll indicate my fastq file. That is what data/ref/dm6.fa. I'll indicate my GTF file, which is data/ref/dm6.atf. I'll specify another option here, which is genome SA index n basis. I'll say 12. So we have everything ready. Okay, so we are going to exit this editor, and we're also going to save the changes. Okay, so now let's do an ls, and we will find the file there, this script here. We are now going to add execution rights. So we will say chmod +x, then we specify the file name. Now we are going to execute the scripts. Then this will generate the index file. So let's do that. I'll say // then I'll call the file. So now star has started its work. It's now going to generate the index files. Okay, star has done its work. So let's check the output files. Let's do an ls just to check some stuffs here. So we will now ls into the index directory. So I'll say ls index, and I'll see my output files here. So that's what we have. So now we are ready to map the RNA sequence to the reference sequence. We are now going to map the RNA sequence to the reference sequence. So let's take a look at the files again. So I'll say ls data/fastq. So I have the files here. I have two samples. We are dealing with paired end read, so this pair belongs to one sample, this pair belongs to another sample. Let's create a directory called map. So I'll say make the mapped. I'll ls to check that directory. This is the directory, and this is the directory where star will save or store the output files. Now let's go to the star documentation page and look at the instructions we can use to map the reads to the reference sequence. So let's go. So if you're on the page, just scroll down. This is page 5. So click more pages, then go to page 7. So this is 6. Let's go to 7. Then you will see this section here, running mapping jobs. So if you want to map reads to a reference sequence, then you need to call star, and you also need to indicate some options here. We have some of the options here. So we will specify all these options, these 3 options, and I'm going to add 2 more options. I have run thread n to specify number of threads, genome DAR to specify the directory which has the index files, and we also have read files in to specify our fastq files. If you are dealing with single end reads, it's read 1. If you have paired end reads, then we have read 1 and then read 2. So let's go back to the terminal and then perform the mapping. So we will create a script, and then in that script we will place in the star command that we'll use for the mapping. Okay, we are on the terminal now, so I'll create a script. You should also take note that we are dealing with more than one sample. So we need to find a way to automate the mapping process. We need to find a way to make the script generic so that we can always factor in the different samples that we have. So I'll open the script. I'll say nano map_reads.sh. I'll start with my shebang line. Then I'll move to the next line. So here I'm going to define, or I'm going to give variables. So these variables will assign the file names to this variable. So we'll use read1 and then read2. Let's take a look at the files again, the fastq files. So I have data/fastq. This pair belongs to one sample, this pair belongs to another sample. So for each sample, we have read1, read2. If you're dealing with pair and reads, then there's going to be a character or groups of characters that will differentiate, or that will be used to differentiate between the forward and the reverse reads. So in this case, we have 1 and 2. So 1 indicates forward, 2 indicates reverse. So we have that there. So what we are going to do is to create variables for both read1 and read2, and then we will use that to process our data. So I'll start with read1. So read1, and I'll say equals. So I'll come back and then I'll pick the first sample, which is this one. So I'll pick the sample name, the base name here. I'll copy it and I'll send it here. So I'll say data/fastq/ and I'll place in the ID, the name. And I'll say _1.fastq Sanga. This is read1. Read2 becomes data/fastq. Then I indicate the same ID or name, and then I _2.fastq Sanga. So what we have here, we can always edit this and then place in our files and then still execute the scripts, and then we can get our job done. So let's specify the options we use for star. So I'll say star, and I'll say --run. So it's this way, star --run n. I'll say 8. I'll bring my slash and then I'll move to the next line. So the next line, I'll say --genome dar. Then I'll say index. This is the directory. Say slash again. I'll move to the next line. So the next line, I'll define my files. So I have --read files in. Then I'll say $read1 and then $read2. So look at what I have. This is $read1, this is $read2, because we have created the variables here. This is read1, read2. So the $read1 means that we need to use the actual values that were assigned to this variable. So here, it makes it possible for us to reuse the scripts without having to write all the commands again. All that we have to do is to specify the file that we want. Okay, so this is the file name. So we have 2 samples, this and this. So now I'm starting with this. So if I finish with that one, I will now come in and change the ID. I will use this one. So I can come back, change this ID to what I want, and then execute the scripts. So that's what you're going to do. So there's one way to automate commands, and there are other ways to do it. If you have lots of samples, you can use for loops as well. And you can also combine the for loops with some Linux commands to get all the files and then process them. So if you are interested to learn about how to automate scripts or how to run mapping activities when you have multiple samples, we have lots of samples, you can always reach out to me and we can have a session together. So just make sure to contact, because ideally, if you are doing RNA Seq data analysis, you may have lots of samples. Maybe you may have 10, 12, maybe 20, etc. So you need to find a way to automate the process. This approach here, I wouldn't recommend it if you have lots of samples, but because we have 2 samples, that is why I'm using this approach. So take note of that. I'll also make the scripts that I'm using for this exercise available. So if you want to start practicing in this tutorial, if you want to reproduce this tutorial, you can check the description box. The link to the scripts will be given there. So let's proceed. So I have my read files also specified. Then I'll also specify this dash dash out some type. I'll say bam. I'll say sorted by coordinates. So here what I'm saying is that I want the output file to be of the BAM formats. I want a BAM file basically. That's what I'm saying. We have some files, we have BAM files. So I want the BAM file. So that is why I have the BAM here. And I also want it sorted by coordinates. So that's why I have this also here. So I will now do this. I'll come here. I'll say dash dash out file name fix. This is what I'll use to specify my output file names. So I'll say mapped slash, then I'll say GSM. This ID here. This is what I want. Okay, so now I have the script complete. So I will exit and save the changes. I will now use this to add execution right. So chmod +x map, that's called reach.sh. So I will do that. So now I can execute the script. So I'll say /map reach.sh. So this will perform the mapping. We specify this sample here. So that means we are going to map this reach to the reference sequence. So let's run this command. Okay, star has finished mapping the first sample. So let's proceed. So I'll say ls, then now ls into this directory, the map directory. So I'll say ls mapped. Now see the files there. So I have the output files here. So this is the BAM file, and we also have some log files here. This, and then we also have this one here. I've already explained these output files in another video, so you can check that video out. The link to that video is in the description box. You can also watch that video by the link right up here. So for this tutorial, I'm only going to focus on the BAM file here, and then we will just display this one also here. But let's map the other sample as well. So let's edit the script again. And this time we are going to use this ID here. So let's first copy it. Then I'll say nano map underscore reads. And this time I will change this sample here, this ID here. That's what I'm going to do. The same goes for this one. So now I have the second sample. So you notice that I only modified the sample IDs here. All other commands are the same, because here this one represents what we have here. So whatever you put here is what will be used here. So let's map this other one too. And let's check this one too. We need to specify this and give the same sample name. So let's do this. So now we will do the mapping, and we also have the output files for this sample. So let's save the changes. So let's map again by calling the scripts. Okay, so star will map the second sample also. Okay, star has completed the mapping activity for this other sample. So let's check the map directory. Let's do an ls, see what we have. So we have all of them here. Okay, so we have them nicely done. So we can always look at the output files, and we can always differentiate them using the sample IDs. So we can proceed. So for the star output, this is the BAM file. There's also a log file for the mapping statistics, which is this one here. So let's just take a look at the mapping statistics for these samples. Let's check. Let's try with this one here, So I will say it's a text file. So I'll use a Linux command to display. So I'll say cat mapped, then I will specify that one, which is here. So I'll open this one. This is for the 177, the sample which has the last three numbers as 177. So I'll open this and I can check the mapping statistics here. So I'll focus on the uniquely mapped reads, which is this one here. It's what, in terms of percentage, it is 82.20%. Ideally, we should have most of the reads, majority of the reads mapping to the reference sequence. We should have a high percentage. That is what we see here. So things are looking good. Let's look at the other sample. So I'll indicate that also here. And let's take a look at that. So that one too, we have the number here, percentage is 75.58%, which is also high. Okay, it's also high, so it's good. So we have high percentage. So we have high percentages for both samples. So that means that we are good to go. Now with the log file, with the mapping statistics, you can also aggregate them, then visualize all of them. Okay, so there's a tool called MultiQC. You can use that to aggregate this mapping statistics, then check all of them out. So, and also that can help you to easily compare them. Okay, because if you are dealing with lots of samples, it becomes very cumbersome trying to open each of these files and then reading them. So MultiQC can be used to make your work easier because it will aggregate all these reports together into a single file and also generate some plots that you can use for the analysis. So I will encourage you to use MultiQC for your QC. So that's about it. So let's proceed. So let's take a look at the map directory again. And this time, what we are going to do is that we will use the BAM files. That's what we are going to use for the next activity. So let's continue. We are now going to count the number of reads that were assigned to each gene. In other words, we are going to perform gene quantification. We are going to use FeatureCount to do this. For the FeatureCount command, we are going to use the options that were stated in the Galaxy tutorial here. So we have the FeatureCount section and we have strand information. We have the annotation file, which is used to specify the GTF. We also have options for paired and reads. We are going to use this option. We also have the minimum mapping quality per read, which is 10. We will use that. We're also going to use these options here. So that's what we are going to do. And after that, we are also going to aggregate the results using MultiQC. So let's go back to the terminal and then run the FeatureCount command. So we will call FeatureCount and then we will supply the BAM files to it, this one and then this one. Before we do that, let's first create a directory. So we will say make the counts. So this directory is where we will store the outputs. So now we have a directory created. So we will say FeatureCounts and then we'll say -T8 to specify the number of threads. We will now specify -S0. -S is used to specify the strandedness. So here 0 means unstranded. With the strandedness, you can have one of three values: 0 for unstranded, 1 for forward, and then -1 for reverse stranded. All right, so unstranded you represent with 0, forward stranded you represent with 1, reverse stranded you represent with -1. All right, so that's how you need to do it. with the strandedness, you can estimate it by visualizing the BAM files. So if you visualize using tools like IGV, it's possible to estimate or identify or have an idea of the strandedness, and you can use that to specify the appropriate value. There are also tools available that can help you to estimate the strandedness. All right, so one such tool is made available, or let's say it's made mention of in the Galaxy tutorial page, the tutorial that I based this very tutorial on. So that Galaxy tutorial page has a tool that also allows you to estimate the strandedness. So just make sure to check that tutorial out and you'll find the tool there. All right, so there are other approaches that ideally these two should serve as a starting point for you. All right, now we need to specify another thing. We are dealing with paired and width, so we need to specify -p, then --count read pairs. We also need to specify the feature of interest, so that's -t exon. We want to use the exon. I think that's even the default. With the identifier, we are going to use gene ID, so we say -gene _ID. We are also going to specify the minimum mapping quality. So we'll say -q, we will use 10. We are also going to specify the annotation file. All right, so here we are referring to the DTF file. So the DTF file, we can find it in the data/ref/dm6.dtf. All right, so we are going to specify it. So to do that, we say -a, and we say data/ref, and we specify the GTF file. So this is it. We also need to specify something else. We need the output. All right, so output where the output file should be. All right, so that's how we are going to specify it. We say -o, and we specify where the output file should be stored. So it's going to be in counts. Remember, we created a directory called count, so we are going to specify that's there. All right, so we say count / and we have to give a file. Now, because we want to get a read count for this sample, GSM 461177, the output file should reflect that name. All right, so we are going to say GSM 461177.count. That's going to be the file name. All right, so that's it. So count/GSM 461177.count. That will be the output file name. So this output file will have the information, okay, for the read count for that particular sample. All right. Now we also need to specify the BAM file. So the BAM file that we need to specify, we should have it here. So we have to specify. So we say mapped / and we specify the BAM file. All right, so there's the BAM file. So now we will run FeatureCount. Perfect. So now FeatureCount is doing its work. All right, so it's currently working. Now this is fast. Okay, so again, FeatureCount has done its work. So depending on your computing power, it will take some time to be fast. All right, so this one was pretty fast. It was very quick. So we have the information we need here. So let's proceed. So we will clear the screen and continue. Okay, so now when we do an ls into the counts directory, we are going to find the output files for this sample. So we have that here. All right, so we can just do a cut into the count. Let's see how it looks like. So I'll just say cut count/gsm.count. Okay, the full file here. So gsm 461177.count. So this will give you everything here. So you have lots of information here. All right, so it tells you the count. There are other information here, so I will actually leave the documentation to feature counts, okay, so that you can read more about the outputs, but we are going to explain them also later on. Okay, so this is how it is. Now for the summary file, which is also good if you want to get an overview, that one too is here. I'll just say counts. I'll specify the file. Okay, so we have .count.summary. So this will display the count file. So this gives us a summary. So we have assigned reads. This is a number. You have unassigned, unmapped, unassigned read tab, etc. Unassigned multi-mapping, etc. So we have all these here to let you know the various counts for the assigned features, the features that feature count identified, and the read counts that have been assigned to them. So this is for this sample. So this particular one is possible to also visualize. All right, so we can visualize this, but before we visualize, let's run the next sample and then we can visualize and see what that also is. Okay, so you run the other sample, which is 1180, and after that we are going to visualize the result for both, and then we can see how feature count also make things easy for you when combining reports. All right, so let's clear the screen and then let's run feature count for the other sample. Okay, so I'm clearing the screen and then I'll record the feature count command for the first sample. So this is it. So since we are going to do this, we are going to specify another sample. We need to clear this and we also need to clear the output. All right, so we are clearing both. So since we are now going to run for the sample 1180, so -o would change and then the input file would change. All other options remain the same. All right, so it's only the output file and the inputs that changes here. So for output, I'll say count/gsm 461180 dot counts. And then the input will be mapped /gsm 461180, and we specify the bound file. So let's run this command also. Perfect, that has also been done. So let's clear the screen. Let's ls into count, and we are going to find that one also here. All right, so we have them also here. Now let me also say that the output, okay, this output, the counts we have, both summary and then the main count, you can visualize, or before I even talk about visualizing, let me say you can view using a spreadsheet software. I will show you how that is done. But first, let's just look at the summary for the sample 461180. So I'll just do a head, or I can even say cut because for the summary, there's not that much, but this one, head. So I'll say head count gsm 461180.counts. This one I'll just do a head because you have a lot of information. So this is it. All right, let's clear the screen. Let's look at the summary also. So the summary, down I'll say cut count gsm 1180.count.summary. That will give you the summary as well. So we have them here. So I repeat, you can also view these files using spreadsheet software. All right, so we shall view with spreadsheet software later on. Okay, so in the course of the video, in the course of the tutorial, we are going to do that. Now let's take a look at something. So you have this, we have two samples, by the way. So we have read count for two samples. You could also have a situation where you have more than two files or two outputs, i.e. more than two samples. All right, so in that situation, it will be useful to be able to aggregate these reports into a single report or a single file that you can read. All right, so what we are going to do next is to aggregate these two reports, and then we are going to view them as a single report using MacOS. So MacOS allows us to aggregate our reports so that we can view them and also compare them to one another. All right, so it's very convenient to do some of these things. So for those who are curious, so this is the homepage for MultiQC. I've covered some tutorials on it, by the way, so you can check them out. So it helps you to aggregate report from different bioinformatics tools, okay, or from different bioinformatics analysis. All right, so it's combined them into a single report, and you can always view them. All right, so not just a single file, or not just a single tool. Let me put it that way. Not just a single tool. You can have report from different tools in different files, and you can combine all of them into a single file and then read. All right, so MultiQC automatically identifies the kinds of reports, and then it formats it accordingly so that you can have your reports and then read them, or basically explore or examine or interpret them. So it helps to make things easy for you when it comes to aggregating reports or results. So the link to this tool is in the description box. I'm in the documentation for MultiQC, so you can check it out later on. Let's get back to our data. So what we are going to do is to aggregate these two reports together. All right, the report for the two samples using MultiQC. All right, so to aggregate report, let's say you have your FeatureCount reports in a directory. So this is my directory, and I have my FeatureCount reports. All right, so I have this, and then this. These are the summary. Okay, so these are the ones that FeatureCount will use. So let's say I have this, and I want to aggregate using FeatureCounts out, and not FeatureCount. So let's just say I want to aggregate using MultiQC. All right. So to aggregate using MultiQC, I just have to say MultiQC, and then I will specify the inputs. So here my inputs are in the count directory. So I'll say counts, and I'll say star.summary. All right, so you can also say star. MultiQC will automatically identify the files for you. All right, but in this case, we want to be specific. So we are using the summary file. So that's what I'm specifying here. So I'll say MultiQC count/star.summary. So that means all files that end with .summary. I have two of them. So I'll run this command, and then MultiQC will aggregate them for me. Okay, so it tells me it has found two files, or let's say two reports. So once it identifies them, it will aggregate them for you, and you have your output. So that's what I have. All right, so once it's done, I can check it out. Let's do that now with my file manager. So this is the file, so I can open it, and when I open it, I'm going to see my reports. Okay, so I have my two samples, 1177 and 1180. So I have them here, and then we have the plots. So it tells you the plots. We have this plot here, we have some colors, and it gives you the meaning of the colors. So here, the blue here is for assigned reads. We also have unassigned multi-mapping, which is here. All right, so let me just enlarge it a bit. We have unassigned multi-mapping, black, unassigned no features. You have this color, unassigned ambiguity. So you have them here. So this allows you to also easily understand and even sometimes interpret your reports. All right, so you have your visualization, so now it becomes easy to interpret. It becomes easy to study. It becomes easy to understand what is going on here. All right, so, and also because it's a plot, we are also able to compare because of how it has been displayed for us. So we can compare. So if you compare, let's say these two samples, we see that with these two samples, so here, assign number of reads. If you hover your cursor, it gives you the number 827644. Here it says 887437. So that's how it is. Okay, so this gives you an overview, and it will help you, and in some cases even enable you to identify if there are issues with your data or not. All right, so that is what we have for the MultiQC. All right, with respect to FeatureCount reports. All right. Now let's do this. Let's go back to our data and then do something else. If you take a look at what we did, all right, we had to run feature count twice. We had to run it for the individual files. Let me just do it here for you again. So let's take a look at the files. All right, so we have them here. So we had to run the individual commands. So we had to run the command for 1177, and then we had to run it again for 1180. All right. If you have several reports, or let's say if you have several BAM files, let me just put it that way. If you have several BAM files, you don't need to run the feature count command one by one. You can use the wildcard to specify all the BAM files and then run it again. So what I'm going to show you is how you can run feature count and specify all BAM files. If you have several BAM files or multiple BAM files, I'm going to show you how to run feature count once, all right, so that you don't have to worry yourself running the commands one by one. So in that situation, we still maintain the options. Okay, we maintain everything here, but then the outputs and then the inputs changes. So this first group of codes or commands will remain the same. So what we do is that if you have multiple BAM files, all right, then what you have to do is to say, let me just do it again. For the sake of beginners, I will just try to do everything again so that we can go through them one by one. So I will just do this. Let me just do it this way. So let's say you have your BAM files, let's say mapped. You have your BAM files, let's say ls map. All right, I'm going to do it here. Mapped star.bam. Let's say you have 2 BAM files or 3 or 10 or maybe 50 or 100. If you want to run feature count on all of them, then this is how you do it. You will say feature counts like this, and then you will specify your options. All right, so the options, we use -T8. We said -S0 for strandedness. We have unstranded data. We said -P --count read pairs. That is for what? Paired and reads. We have -T exon. That means the feature of interest is exon. The identifier, we said -gen. We are using gen ID. And then minimum mapping quality, we said 10. Annotation file, that's the GTF, we said -A data/ref /dm6.gtf. That's the GTF file. Then when it comes to the output, all right, you specify a name. So I'll say count/gens.counts. All right, I already have my directory created, so I'll specify a name. So I'm saying gens.count because now I have multiple files, so I should have a name that makes sense. Okay, that's descriptive. All right, so that's what I have here. Then the inputs, I'll say mapped/star.bam. So once you have it this way, then you can run it. So let's execute this command. Perfect. So once you execute it, feature counts will look at the files and then it will analyze and give you the outputs. Let's look at the output. So if you ls into count now, we are going to find what? gens.count. So now you see them here. Okay, so when we ls into count, you will see gens.count. Okay, gens.count summary. Okay, so this has the information. I can say count. I'll say gens.count.summary. And it will give me what? The information. All right, so I have assigned unassigned, unmapped, etc. So it will give that information for the BAM files. Okay, so you have two BAM files or two samples. Let's use BAM files, okay, to make it simple, because we are analyzing BAM files. So for each BAM file, it gives you the status. Okay, so we have that here. So we have this 1177, this is 1180. The same thing for the gens.count file. So let's say head counts gens.counts. The same information. So we see that here. All right. So here. All right. So there's it. Now it's time to actually explore this count file. I made mention earlier that we are going to open it with a spreadsheet software. So what you should note is that this is a tab separated file, despite the extension that I use. Let me just do it again here. All right, despite the extension that I use, that's .count, this is a tab separated file. That means that the columns are separated using a tab character. So you can open it with a spreadsheet software. That's what we are going to do now. I'll show you. So let's go to counts. Yeah, so I'll just open it. I have my spreadsheet software here, so I'll open it for you to see. So this is it. So for the FeatureCount output file, the count file itself, so this is what you have. It tells you the command that was used, which is here. It tells you the column. So we have gen ID, which is here. I will just undo it. For each of the gen, we have chromosome, start and strand length, and then after this we have the different BAM files. So we have this and we have this. All right, so there's it. So when we are going to perform your differential expression analysis, it is this file, the information here, that you will use to do the differential expression analysis. Now let me also say that what the output here, all right, if you look at the names here, see we have mapped/gsm 4611177, etc. Okay, for this BAM file, the same for this BAM file, right? So before you do your differential expression analysis, you will need to do some formatting to make sure the naming is okay, everything is fine, and then you extract just the counts, okay, for the differential expression analysis. Now, depend on your objectives, you may need to also do some analysis using the information here. All right, but then for the differential expression analysis itself, it is the count that you use. Also, for that one, you need to do some further processing. Now, if you have such a data and then you need some help, you can always contact me, book a session, and we can look at how to properly format this data and then run it in tools like DSIC2. Okay, so for differential expression analysis, you can use tools like DSIC2. You can use tools like HR, Lima, etc. All right, so I've covered some tutorials on how to also use DSIC2. All right, now if you have this, then you can also do the multi-QC, and this time what you need to do is to specify just this one here. All right, because you have everything in this file. All right, so that's how we do it. This also, you can also open it with a spreadsheet software. That's also fine. So we just have to know how to do with that. Okay. So I repeat, once you have your file, your output file, you need to do some processing before you can now push it to the differential expression analysis tools to do the downstream analysis for you. Okay, so if you are interested to learn how to perform differential expression analysis using the DSIC2, then watch this video right here.